So now that we've discussed Euler's equation, we're going to move on and talk about Bernoullis equation, which is actually a simplification. And the question is, can we simplify Euler's equation any further? We can actually integrate it. We integrate along a streamline. So we make the assumption of steady state, incompressible, inviscid flow, and we have flow along a streamline. So if you have 2 points connected by a streamline, we can use this result. And then we integrate, and the result is Bernoullis equation. Bernoullis equation basically says that if you add up the p over rho plus v squared over 2 plus gz, it has to be equal to a constant. So it never changes. No matter where you go along the streamline, this sum is the same. So we can take a look at this figure, which demonstrates a concept called Torricelli's law, which defines this envelope line. But we can use this to look at Bernoullis equation. If we have a point here on the surface of the water, we'll call that point 1. And here we have this jet, and we'll call this point 2. And let's just say these are connected by a streamline. If we take point 1 and point 2, they're both equal to the same value, so we set them equal to each other, and then we subtract one side, and we get this equation where we have difference in pressure, difference in velocity squared, and difference in height. So the gauge pressure at both of these points is 0. Both of them are basically exposed to atmosphere, so we can actually say that this term is 0 for this particular problem. It won't be for all problems, but in this case it is. We can actually make the assumption that the reservoir is very large compared to the jet. So that means that V1 is much, much smaller than V2, and then we square it. So V1 squared is much, much, much smaller than V2 squared. So we can say we can neglect V1. Now it's not actually 0, but it's so much smaller than V2 that it's approximately 0 compared to V2. And then we can measure the height, or delta Z. So this would allow us to calculate V2 for this jet, the velocity of the jet coming out from this reservoir of water. So you can actually go and check out this simulation and look at the water tower and the flow simulations to observe how changes in pressure, velocity, and elevation affect each other, and see how the Bernoullis equation works in practice. Now the question we have to ask ourselves is, what does this equation actually mean? We integrated a force over a distance along the streamline. So these force times distance is work. So these terms represent pressure work, change in the potential energy due to pressure, acceleration work, or change in kinetic energy, gravitational work, which is the change in the gravitational potential, and so on. So this equation actually balances the kinetic energy with the potential energy, which means there may be another way to think about this problem. We can also obtain Bernoullis equation from the first law of thermodynamics. So we start with the first law, and we assume steady state and incompressible flow. So steady state lets us ignore the time derivative part. We're also going to make the assumption that there's no heat transfer, and that there's no work being applied to the fluid. There's no shear work because the velocity at the wall is 0 in this case. So we can ignore all those work terms. Now, once we've done that, we can simplify it out. We can expand the total energy into the internal energy, kinetic energy, and gravitational potential. And we can assume a single inlet, single outlet case. So we add up the value at the inlet and the value of the outlet. And we can say that rho VA, is the mass flow rate, is the same on both sides, so we can cancel that part out. So then if we do our single inlet, single outlet, we say 1 and 2, and we can recast this equation. And this is familiar. This looks much like the Bernoullis equation. But we have an additional term here. We have this difference in internal energy. This term represents the mechanical energy that's been converted into heat by friction, essentially by the viscosity. So in a real fluid, you lose energy from the mechanical energy of the fluid, and that gets converted into heat. So the fluid heats up. And that's this difference in internal energy. Now, if a flow is inviscid, if it has no viscosity, then there's no friction. And we can say that this internal energy change is 0. And then we can recover the original form of the Bernoullis equation. Now, it's important to note that deriving the Bernoullis equation this way means we don't have any requirement that there be flow along a streamline. So now we can connect any 2 points in an inviscid fluid and apply the Bernoulli equation between those 2 points. They don't have to be connected by a streamline anymore. Now, Bernoulli's equation may be one of the most abused and misused equations in fluid mechanics. We have to be very careful when we're using Bernoulli's equation to make sure that the assumptions are valid. The incompressible, inviscid, steady state assumptions. So we cannot use this for flows at sharp bends or across edges because inviscid flow is no longer valid. If we have a long pipe or something like that, friction is no longer negligible, so we cannot use it for these long distance types of flows. Anytime you have shock waves, you have violent mixing, and then again, those types of effects become important, and compressibility effects become important. You can't apply it through hydraulic machinery because now you're adding work, and our assumption was no work is being done on the fluid. And the fluid has to have a constant density. So that means it has to have a constant temperature, and it has to be an incompressible flow at a low Mach number, typically less than 0.3. So there are some limitations on Bernoulli's equation. We have to be careful. I also want to introduce another concept called the hydraulic head. If we divide Bernoulli's equation by g, we get this equation. And the sum here, the constant, is what we call the hydraulic head, h. It has units of meters or feet, dimensions of length, and it's often used to characterize industrial systems. For an ideal fluid, an inviscid, incompressible fluid, this value will be a constant. H will be a constant. However, for a real fluid, friction decreases the total mechanical energy, so H will decrease slowly as the fluid moves. We can also look at two different definitions. We can look at the energy grade line or the hydraulic grade line. So the energy grade line is basically the hydraulic head. We'll call this the energy grade line. And in the figure, that represents this constant line. And we can see we measure this by measuring the stagnation height of the fluid. We can also define the hydraulic grade line. P over rho g plus z is the hydraulic grade line. So if we just have a tube coming off from the side of the flow, this is the hydraulic grade line. And then we have the stagnation value for the energy, which is the energy grade line. So we can make these two measurements, and we can measure this height difference, and this height difference will be equal to v squared over 2g. So by measuring this difference, we can measure the velocity of the flow, which is a very important concept. We use this concept in the pitot-static tube. So in Bernoulli's equation, we use the thermodynamic pressure. This is also called the static pressure. And we already know that pressure does not change normal to straight streamlines. So if we have this fluid that's moving through a channel, we have straight streamlines, and pressure here will be the same as the pressure all over inside this pipe. We can also define the stagnation pressure, which is the pressure a fluid would have if it were slowed down to a stop without any friction. We measure this with what we call a pitot tube, where we have a small hole in the front, the flow enters, and then we measure the pressure where the fluid has stopped. So now we can measure the thermodynamic pressure, and we can measure the stagnation pressure, and we can compare the energy grade line and the hydraulic grade line. We can actually measure both simultaneously with a pitot-static tube, where you have the pitot tube and the static pressure measurement, and you can measure the difference between those directly. So from the Bernoulli equation, we can go back and we can get that pressure difference, which we can measure directly, is related to the square of the velocity. So we can actually get the velocity is the square root of 2 times the pressure difference divided by density. So in dimensional analysis, we saw rho v squared as a common pressure scale during dimensional analysis. Here, we can define rho v squared over 2 as the dynamic pressure. That's actually got a name. We call it the dynamic pressure. And this allows us to measure the velocity of a fluid directly by inserting this pitot-static probe.